Hello friends, today we will continue our discussion on solar cell. Till now we have seen what is a solar cell structure and how the solar cell operates, right? Today we will be discussing the VI characteristics of solar cell, fill factor, advantages or merits of solar cell, disadvantages or demerits of solar cell. So these we have already completed. Today we will be discussing these four. Okay, just for a recap, this is the structure, this is p type, n type, and this is the junction between them. We have seen that the face which is facing towards sun is much thinner as compared to the other region, right? Here n is a thinner compared to p type. On the top surface, the metal contacts are in the form of fingers. This will increase the surface which is exposed to sunlight, and hence the amount of sunlight absorbed will be more. Now coming to the VI characteristics, this is P side, N side, and these are the metal contacts. When sunlight falls on the solar cell, we have seen that the P side develops a positive potential and N side develops a negative potential, and hence there is a potential difference between the P side and N side. And when we are connecting some load to the solar cell, a current flows through the device, right? Now we will see what is the sign convention we are going to consider when we are plotting the VI characteristics for the solar cell. First we will consider the direction for potential. Here you see the P side we are having positive potential, N side is having negative potential. And if you remember the forward bias condition, there also we used to connect the positive side of the battery to P side and negative side is connected to the N side. And here also the polarity across the solar cell is same as the polarity of a forward bias condition. So this side is positive, N side is negative. And in case of forward bias, we used to take the potential as positive. So here also you will be considering the potential as positive. Now coming to the current direction, this is the direction of the current. If you recall, the direction of the current here is same as the direction we obtain in case of a reverse biased PN junction diode, right? If you want, you can look into those videos in which I have discussed about the forward and reverse bias for PN junction diode and their VI characteristics. That is discussed under the semiconductor physics module. I will also provide you the links in the description box below. So here we saw that the potential is positive and the current direction is same as the direction of reverse bias PN junction diode, and in case of reverse bias we used to consider the current as negative. Basically within the PN junction, if the current is flowing from P side to N side, then that will be considered as positive. And if the current is flowing from N side to P side, then that will be considered as negative current. And here in this case you can see this current is going this way, and within the solar cell it is moving from N side to P side. So this current is taken as negative. So in the graph, if you will see, in the x-axis I have taken potential, y-axis current. Further we saw that the potential is positive, that means the values will come in this direction, right? And coming to the current, it is negative. So this is positive current, this is negative current. So the values of current what we will obtain for solar cell, that comes in this region. And hence we are getting the VI characteristics for solar cell in the fourth quadrant. Let us now understand how to plot the VI characteristics for solar cell. First we will be considering open circuit condition. What is the meaning of this open circuit? This is the solar cell. These are the two terminals of the solar cell. In case of open circuit, this solar cell is not connected to any circuit. It is open, that means this and this terminal and this terminal, they are not connected to any other circuit or wire. So in this case, when sunlight falls on this, we saw that electron hole pairs will be generated at the junction. And once these electron hole pairs are generated because of the depletion layer potential or potential barrier at the junction, they will move to the opposite side. Hole will move towards P side and electrons, they will move towards N side. Now slowly we are getting more electron hole pairs are generated over here, and as they are generated at the junction, holes will move towards P side and electrons, they will move towards N side. So we will be getting holes over here and electrons at the negative or N side of the solar cell. Because of this, slowly the potential over here that is increasing, and hence the difference in potential at the two terminals, that will slowly increase. But what happens after a certain time, if further electron hole pairs will be generated over here, these holes, when they will try to move this side, they will be repelled by these holes. So the further movement of holes will be stopped. Similarly, if this electron tries to move to this side, these electrons which are accumulated over here, they will repel the electron to come this side. That means a equilibrium will be established when further flow of the carriers is stopped. At that time, we will get a saturation of holes here and electrons here. And if there is a saturation reached, then the difference between these two terminals will be maximum, right? And that maximum potential difference is known as open circuit voltage, and it is denoted as V is equals to VOC. This is the maximum potential difference between the two terminals of the solar cell when it is in the open circuit condition. Now coming to the current, what will be the current under this condition? At this condition, there is no flow of carriers anymore from one side to other side, and further it is also not connected to any circuit. So there is no continuous flow of carriers. That means current should be equals to 0. So the current is equals to 0, and this VOC is known as open circuit voltage. Now let us plot this point on the IV characteristics curve. So it is B is equals to VOC. At that time I is equals to 0. I is equals to 0 means we will be getting the point on this axis, right? I is 0. So in this axis, let some point here we are getting VOC. So this is the point we obtained for open circuit condition. Here we got one definition, that is open circuit voltage. This is the maximum voltage across the illuminated junction or solar cell which occurs at 0 current. Now coming to the next condition, that is short circuit condition. We have seen that when the light falls on the solar cell, holes are accumulated on P side and electrons are accumulated on N side. And after a particular time, there is an equilibrium between them and the voltage obtained is maximum, that is VOC. Now under short circuit condition, what we will do, we will be connecting these two terminals with a metal wire. So we are connecting these two terminals over here. There is no resistance in between that. We have just connected the two terminals of the solar cell. As there is no resistance, what will happen to this electron and holes? The electrons will flow through the metal wire to the P side. Okay. So electrons are flowing through the metal wire to the P side. once they reach over here, they will recombine with the holes which are available here. So once they recombine with each other, they will disappear from here. Once they disappear, if you are getting the holes and hole and electron pairs over here, they can move easily to either side. Once the electron reach over, it will go here and it will combine with the hole present at the p side. That means there is a continuous flow of carriers and there is no resistance over here. So their motion is not stopped by anything. We are getting a free flow of carriers from one side to the other side. And if there is a free flow, we are getting a maximum current. But the voltage, as we are connecting this point and this point, the potential here is same as the potential here. And the potential difference is equals to 0. So V is equals to 0, which is obtained when the current flowing through the device is maximum. And this current is known as short circuit current. So under short circuit condition, we saw that the potential difference between the two terminals of the solar cell is equals to 0 and the current flowing through the solar cell is maximum, which is given as ISC and known as short circuit current. Now we will denote this in the graph. Here you can see V is equals to 0. That means we will be getting a point in this y-axis, right? B is equals to 0. So whatever point we will be getting on this axis. And what is the value for the corresponding current? That is ISC. And I have already told you this current is a reverse current. So we will obtain the point here. This is V is equals to 0, I is equals to ISC. So this point is 0 ISC. So the short circuit current can be defined as the maximum reverse current flowing through the solar cell or the illuminated junction when the voltage across the solar cell is 0. In the previous slide, we have seen that this is VOC. That coordinate was VOC and I was 0. So this is that point and this is the short circuit point 0 ISC, right? So these are the two extreme points. We have to obtain the in-between points. To obtain the in-between points, we will be connecting some resistance over here. Here I have considered a variable resistor whose resistance value we can change. Initially, we will keep the resistance value very slow. And what is the property of this resistance? Resistance will always oppose the motion of carriers. In case of short circuit, what we have seen that there was no resistance. These two terminals were connected to each other. So there was a free flow of carriers. Now if we put a small resistance over here, few of the carriers they will stop. Their motion will be opposed by this resistance. If carrier's flow is reduced, then the amount of current flowing will also reduce, right? And if some carriers are opposed to move because of this resistance, that means we will be getting some residual potential over here and over here. That means a small amount of potential difference will be there in between these two terminals. So we will be getting a small voltage and the current is reduced by a small amount. That means a high current. So we will be getting a point somewhere here. Okay. The current is reduced by a small amount and voltage was initially 0. It increased by a small amount. So we will be getting some point over here. And this resistance I have written as RL or load resistance. Now if I increase the value of this resistance little more, then what will happen? Current will reduce further and the carriers which are accumulated here, that number will increase and that will increase the value of the potential difference. That means we will be getting a higher potential difference and a lower current. So we will be getting some point over here. Similarly, by increasing the value of this load resistance, what we are getting? We are getting lesser and lesser current but higher and higher voltage. That means we are going this way, and finally for open circuit means the resistance would be infinity. There is no connection between these two, that means the resistance is infinity, right? So that time we will be getting the voltage between the two terminals as maximum and the current is equals to 0. So we will be getting points like this if we will slowly increase the value of load resistance from 0 to infinity. And if we will connect those points, this is what we are getting the VI characteristics of a solar cell. So for open circuit, there is no load resistance over here, it is open. These two sides are open. That means this load resistance we can consider that as infinity. But for short circuit, they are connected without any resistance, just a single metal wire we connected. So we are considering RL is equals to 0 for short circuit. So this is how we obtained the VI characteristics of solar cell, which lies in the fourth quadrant. Now I will show you the circuit which is used to plot this characteristics curve. This is the solar cell and this is the variable resistance which is denoted as RL. Through this voltmeter we can measure the voltage across the solar cell, and through this ammeter we can measure the current through the solar cell, and after plotting those corresponding values we can obtain this characteristics curve over here. Next I will be discussing a very important factor which is considered as a figure of merit for solar cell. This is nothing but fill factor. First we will understand what is this fill factor. So this is VOC, this is ISC. If I will extend, this is the maximum voltage and this is the maximum current, and we know that power is equals to the product of voltage and current, and the area under this curve should give us the power. So if we will consider the maximum power which should be obtained from the solar cell is equals to VOC ISC, that is nothing but this rectangular area, right? But we have obtained the VI characteristics as this one. So the actual power obtained from the solar cell is not the value is supposed to get by using the theoretical calculations. So the fill factor gives us that ratio. So let us see where we are getting the maximum power. For that, first we will connect this one, and from this point if I will connect, this is the voltage where we are getting the maximum power, and if we will extend the current this direction, so this Im is the current for which we are getting the maximum power, and the maximum power is given as Im into Vm. So this area, this gives us the maximum power. This is what we actually obtain, and this is what we supposed to obtain by using a theoretical calculation, and their ratio gives us the value for fill factor. So the fill factor is the ratio of maximum obtainable power to the product of the open circuit voltage and short circuit current. So the maximum obtainable power is this one, Vm Im, and hence I can write the maximum obtainable power is equals to Vm Im. So using this, the fill factor can be written as Bm Im by VOC into ISC. This fill factor is a measure of quality of the solar cell and is a figure of merit for solar cell design. So this I have drawn in the fourth quadrant, but in books you may get this in this first quadrant over here. This is our ISC, this is VOC, this point is IM, and this point is BM, and this is our maximum power obtained. They are plotting this for convenience to explain, but actually we are getting the plot in the fourth quadrant. Okay, so you should not get confused. Now let us see one more quantity, that is conversion efficiency. This is the ratio of maximum obtainable power to the incident power. Fill factor was the ratio of maximum obtainable power to product of BOC and ISC, right? And here it is the ratio of maximum obtainable power to the incident power. Incident power is the amount of power which is being incident on the solar cell, and this is the obtainable power which is nothing but Vm Im. So the ratio between these two gives us the conversion efficiency eta, that is equals to Vm Im, and P in is the incident power. Now let me extend this curve to the first quadrant and third quadrant. If I will extend to the first quadrant, that is I is positive, V is positive, that means this is under forward bias condition. And coming to the third quadrant, V is negative, I is negative, this is reverse bias condition. So if I will extend these BI characteristics to forward bias condition and reverse bias condition, I will get the curve like this. Now let us compare this curve with the VI characteristics curve of a normal PN junction diode. This is a photodiode. Solar cell is one type of photodiode. So this is the VI characteristics of a photodiode. But coming to the VI characteristics of normal PN junction diode, this is the forward bias condition and this is our reverse bias condition. So here you can see that this is somewhat like this, and the curve is now shifted downward, and this amount of shifting, that depends on the amount of incident light energy. If the amount of incident light energy is more, then this shifting will be more. Here we have seen that the VI characteristics of photodiode is shifted down from the VI characteristics of PN junction diode. Coming to advantages of solar cell, it is a clean or green source of energy. It uses renewable energy, that is solar energy. No pollution, hence environment friendly. We are not getting any pollution over here. Like if you burn petrol, coal, etc., you will be getting pollutions. But here in case of solar cell, we are not getting any pollution, and hence it is environment friendly. Easy installation, low maintenance and operating cost. Installation cost initially is very high, but once it is installed, after that the maintenance fee is very less and the operating cost is also less. It does not produce any noise, like if you put some generator or something, they will be producing noise, right? But here we are not getting any noise. It lasts for many years. Once installed, it will work for many years. So these are some of the advantages of solar cell. Now coming to the disadvantages of solar cell, the energy cannot be produced during rainy, cloudy days and during night time, because it requires solar energy, right? Or the light coming from the sun is used to initiate the process, and during this rainy season or cloudy days or night times, there is no sunlight available, and hence energy cannot be produced during these times. Cost of installation is very high, and to obtain high powers we require large area, so it uses large areas. These are few disadvantages of solar cell. Coming to applications of solar cell, it is used in low power devices like calculators, wristwatches, etc. Solar cells are used for transports like car, trains, etc. because here we can use solar batteries to run the vehicles. It is used in storage batteries, street lights, water heaters, irrigations, etc. are also solar powered. It is useful for remote areas, satellites and space vehicles. Many lighthouses are powered by solar cell. Lighthouses means from where we can navigate the ships, etc. So those lighthouses are also powered by solar cells, used for domestic power supply as well. These are few applications of solar cell. Many more are there. Hope you enjoyed the journey of solar cell. Before completing today's video, let me show you some previous year questions which are asked on solar cell. So this is a question which was asked in December 2018. Explain with neat diagram the construction and working of solar cell. State few disadvantages of solar cell, which was of 7 mark. The second part was with relevant plots explain VI characteristics of a solar cell. This is for 3 marks. So this came in JNTU exam in December 2018. One more question which came in May 2019 is, what is a solar cell? Explain with a neat diagram. Define the efficiency and fill factor. Hope after going through today's video and the previous video, you can answer all the 3 questions. Thank you all. If you like the content of the video, please press the like button and share the link with your friends. Do subscribe to my channel to get the notifications whenever I am uploading the new video. Thank you all.